Hello friends, welcome back. Hope all are you doing good and enjoying happy learning. So today in this session we will start with the next case, that is case number 2, where the fin is of finite length and insulated at the tip. Previously we have seen the case number 1 where the fin was of infinite length. So do watch that video, then only watch this because it will help you for a clear and better understanding. So let's start with the derivation. So here what is given? A fin is given. So here you can see in the figure a fin is given. It is attached to a base. Let the temperature of the base be Tb and this be the fin. So the length of the fin is mentioned as L. Previously we have seen the fin which was of a length infinity. So now this is the diagram. So what is happening? So this is the temperature profile. Atmosphere is maintained at a temperature of Ta. So from the graph it is clear that the temperature decreases as the length of the fin increases. But here you can see that the temperature has not attained the atmospheric temperature. So this is a good option, because if the temperature of the fin attains the atmospheric temperature and if we still go on increasing the length, then that part of the fin will be of no use to us. It will just add the material cost and it will be not economical. So it is suggested that we should keep the length of the fin as infinite and proper length should be selected accordingly. So just focus on the derivation now. So here what is given, that the fin is insulated at the tip. This is given. So here you can see this is the tip. Now this tip is insulated, means what will happen? There will be no flow of heat from the tip. It will be neglected as it is insulated. So we have seen this equation, theta is equal to C1 e to the power mx plus C2 e to the power minus mx. What is this? This is the solution for the general solution for the second order differential equation, right? So this is the solution which we have seen in the previous derivation. So go and watch that derivation, then only it will be very much helpful to you. Now the same steps we will apply the boundary conditions. So at x is equal to 0, so this what will be the temperature? The temperature will be nothing but the base temperature, that is Tb. So at x is equal to 0, what is T? T is replaced by Tb. So if I replaced theta here by theta b, I can use theta 0 also. It's up to you. You can use anything. So what I get? Theta 0 is equal to, what is theta? Theta is nothing but the excess temperature. This we have seen, that is nothing but Tb minus Ta, that is this base temperature minus the surrounding temperature. So now if I put x is equal to 0 in this equation number 1, what I get? Tb minus Ta, that is equal to C1 plus C2, that is equal to theta b. So this is the same equation that we have seen in the previous case. So this case, that is at x is equal to 0, it remains same for all the cases, that whether it may be case 1, 2 or 3. Now our major focus will be on x is equal to L. I hope this is very much clear. After substituting you get theta b. Theta b is nothing but the temperature at the base. So this is you get the value of C1 and C2. Name this as equation number 2. Now the major part is at x is equal to L. This is a new part for you. So at x is equal to L, what I have told you, that there will be no transfer of heat. So that means Q is equal to 0. So now as per the Fourier's law, what is Q? Q is equal to, what I can write? Q is equal to minus Ka. If I write minus Ka multiplied by the temperature gradient. So that is nothing but dt divided by dx. So if I want, sorry for the writing. So if I want this Q is equal to be 0, then what should be the case? Obviously this is 0. K and A, these are the constant values. So this can't be 0, right? So what is the only term left with you? That is nothing but dt by dx. That should be only equal to 0. And what is dt by dx? It is nothing but, we can write it by d theta by dx. That is equal to 0. So at x is equal to L, we get this condition as d theta by dx is equal to 0. So this is the only new thing that you are supposed to keep it in mind. Rest the derivation is just simple mathematical substitution. The derivation is little bit lengthy, so just pay attention over it. I hope how this has come is clear to you. Now what we will do, we will differentiate this equation number 1. This is the equation. We will differentiate it with respect to xy because we are supposed to find out the value of d theta by dx. So after differentiating, what I get, c1 is constant. So this goes down, that is m multiplied by c1 e to the power x plus this minus sign, it goes down. So that is minus m, it goes down. So here it is minus c2 e to the power minus x. So now using the boundary conditions, you know that at x is equal to L, d theta by dx, that is equal to 0. So what you will do, you will substitute this value over here, right? So after substituting, you get this is replaced by 0, that is equal to m multiplied by c1 e to the power ml. So here x is replaced by L. Similarly, minus m c2 e to the power minus ml. So if I rearrange this, what happens? This m and this m gets cancelled, and I can find the value of c2 in terms of c1. So this is the value of c2. c2 is equal to c1 e to the power ml divided by e to the power minus ml. So name this as equation number 3. Now what you will do, you will substitute the value of this c2 in this equation number 2. So from here, what is our next aim? Our next aim is to find the value of c1. So all of you know that c1 plus c2, that is nothing but theta b, or you can also write it as theta 0. So c1 as it is, c2, what is this? This value you will substitute, c1 e to the power ml divided by e to the power minus ml. So now what I will do, I will take c1 as common. So in bracket I get 1 plus e to the power ml divided by e to the power minus ml. That's all. What I will do, I will just arrange it. So after necessary arrangement, or we will get this equation. So our next task is to find the value of c1. So just arrange this equation, that is c1 is equal to, this goes here, okay, this will go over here, right? So theta is equal to c1 is equal to theta b multiplied by, in bracket, e to the power minus ml divided by this whole term, e to the power minus ml plus e to the power ml. So we have found out the value of c1 and c2 now. Now substituting the value of c1 in equation number 3. So I will show you the equation number 3 now. This equation number 3. So what you will do, you know the value from this c2. We will substitute the value of c1. So c2 is equal to c1. This is the whole value of c1 multiplied by e to the power ml divided by e to the power minus ml. So after necessary arrangement, okay, what I will do, this theta b is taken as common. So what will happen? This minus ml and this minus ml, it gets cancelled. So what you are left with? You are left with this term divided by this term. So that is e to the power ml divided by e to the power minus ml plus ml. So name this as equation number 4. So we have found out the value of c1. We have found out the value of c2. Now substitute this both values in equation number 2. So let's see what is equation number 2 for your understanding. This is the equation number 2, that is theta b is equal to c1 plus c2. So I will substitute over here, right? So theta is equal to c1. What is the value of c1? Theta b multiplied by this whole bracket plus what is the value of c2? Theta b multiplied by this whole bracket. So what I will do, just I will take this theta b is common now. Okay, here you can see I will take it as common and take it to this side, to the other side as a numerator. Now here this is common, the denominator is common. I can take it common, both the terms. So what I get, e to the power ml plus e to the power mx, okay, plus e to the power ml plus minus mx. So what I will do, this ml term and this ml term I will take common, just simple calculation, and this mx and this mx I will take common. So what I get, e to the power minus m I will take common from here and here. What I am left with? L minus x. Okay, from here and here I will take the minus common. So just I will repeat for you once again. This term minus ml and this mx minus mx. So this I will take common, m as common, and what I get, L minus x, and plus this is positive and this is positive, so I will take this as common. So what I get, e to the power m in bracket L minus x. So you get this equation, right? I hope till here it is very much clear. Just simple mathematical arrangement is there for easy understanding. Now there is one formula that e to the power x plus e to the power minus x divided by 2, that is equal to cos hyperbolic x. This is the formula that you are supposed to keep it in mind. Very important formula. Okay, so here we are having the term e to the power minus x. Okay, this whole term here, x represents this whole term, plus e to the power plus x and this whole term, right? So if this is the case, then we can substitute it by cos hyperbolic x. So what I will do, I will take this 2 to this side. So what I am left with, this equation. So I will substitute this equation by cos hyperbolic h, that is 2 cos hyperbolic h. So what I am left with, theta divided by theta p, that is equal to 2 multiplied by cos hyperbolic, what is this? This whole term, it is replaced by x. So x is what? We are replacing x by this whole term, that is m in bracket L minus x divided by same here, cos hyperbolic x. So x is replaced by this term, that is nothing but ml. Okay, so this, after rearranging it, theta is what? Theta is nothing but t minus ta divided by this theta b. What is theta b? tv minus ta, that is equal to cos hyperbolic m multiplied by L minus x divided by cos hyperbolic ml. So this equation number 5 and 6, they represent the temperature distribution for a adequately long fin with insulated at one end. So I hope the temperature distribution is very much clear. Simple mathematical arrangement is there. So just go through the derivation clearly once again, so you will get the clear understanding. So we have found out the temperature distribution now. Now our next task is to find out the heat flow from the fin, right? So the heat flow is given by Q is equal to minus K AC. This is the cross sectional area divided by dt by dx, right? So at x is equal to 0. So what we will do, we are supposed to find out the value of dt by dx. So we will do what? We will differentiate this equation number 6. Okay, the differentiation is little bit lengthy but very simple. So what we will do, we will replace this t minus tv by theta b. Okay, so t minus ta in bracket, that is equal to theta b, and this is the whole bracket. Now what we will do, we will differentiate this because we need the value of dt by dx at x is equal to 0. So if you differentiate this, so this automatically is not related, so it will be omitted or neglected. So dt by dx, that is equal to, so this is constant, cos hml, here no x term is there, so automatically this also will be constant. Now what we will do, we will only differentiate this because here you are having the x term. So derivative of cos hyperbolic h is nothing but sine hyperbolic h x. Okay, so it is sine hyperbolic x. So the derivative of cos hyperbolic x is nothing but sine hyperbolic x. So this whole term is nothing but your x, for example. So this is sine hyperbolic h in bracket m in bracket L minus x. So this is one part multiplied by, you are having this bracket which is related to x term. So automatically m and L is constant, so it will be 0. M is also constant, so it will be out of the derivative. So this will be 0, and what is the derivative of x is nothing but minus x, minus 1. So what you will get, minus n. So this minus will go to this side. Okay, here you can see. Clear? So dt by dx at x is equal to 0, what you get? Minus theta b multiplied by m in bracket sine hyperbolic h ml divided by cos hyperbolic ml. Okay, very simple to understand. Why? Because I have put x is equal to 0 over here. So if I put x is equal to 0, automatically this term will be equal to 0. And what you are left with? You are left with only ml. So you get minus theta b m sin hyperbolic h ml divided by cos hyperbolic h ml. Now sin hyperbolic h divided by cos hyperbolic h, all of you know it is nothing but tan hyperbolic h ml. So now substitute this value in equation number 7. So what you get? This is the equation, all of you know. Q fin, that is equal to minus KAC dt by dx. So we have found out the value of dt by dx. So at dt by dx, we will substitute this value, that is Q fin, that is equal to minus KAC into minus theta b m tan h ml. Okay. So all of you know that we have seen this also. What is m? M is nothing but under root hp upon KAC. So you get Q fin, that is equal to KAC multiplied by theta b. Okay, this minus and minus sign, it gets cancelled. So multiplied by theta b multiplied by m is what? We are writing m as under root hp upon KAC into tan h ml. So what will happen? You get this equation. If you do the calculation, mathematical calculations over here, automatically this under root sign will get cancelled and you will get the formula Q fin, that is equal to theta b multiplied by under root hp upon hp into KAC multiplied by tan h ml. So you are supposed to keep this in mind, this formula. This tan mh is the extra term in this equation for adequately long fin which is insulated at the end. So I hope you have got a clear understanding of the derivation. What we have found out? We have found out the temperature distribution and the heat flow from the fin, right? So in the next lecture, we will see the third case. Till then, keep watching. Happy learning. Thank you.